energy diagrams, which is a simple method to represent the energy transfer that occurs during a chemical reaction. You need to be able to classify a potential energy diagram as exothermic or endothermic, compare the relative amounts of stored energy of potential energy of the reactants to the products, and then also label various regions of the potential energy diagram. So let's first take a look at an exothermic potential energy diagram. And in a exothermic potential energy diagram, when we look at these, there's always the two platforms which are connected by a hill. The platform that always is closest to the y-axis represents the reactants, and the one farthest away represents the product. The hill describes what's going on with energy when you're climbing up the hill, absorbing, storing more energy, going down the hill, using it, releasing it. So when you look at the two sides of the hill, in an exothermic process, reactants release more energy than they absorb. And as a result, the products, if we had scaling on here, the product's potential energy or stored energy would be less than the reactant. So the product's potential energy is less than the reactants. Calculating a delta H. So a delta value, any type of delta value, is always equal to the final minus the initial. So the ending value minus the initial. Well, in a chemical reaction, products are where we end up. Reactants are what we start with. So the delta H value is the product's potential energy minus the reactant's potential energy value. And in an exothermic process, if you put this in your calculator, the delta H value will be negative. So now, these different arrows represent the regions that you're going to need to be able to label. So just get them memorized of what they represent. So arrow 1 starts at the x-axis and it rises up until it hits the platform that we labeled R for reactant. So arrow 1 represents the potential energy of the reactants. I want to skip to arrow 5. Arrow 5 is like arrow 1. It starts at the x-axis, and where it's a little different is that it ends or extends to the platform that we label P for product. So arrow 5 represents the potential energy of the products. The next arrow I want to take a look at is arrow 4. Arrow 4 is different because it doesn't touch the x-axis. Arrow 4 is the region between the reactants platform and the products platform. So arrow 4 represents the delta H. And one of the main things that we'll see it called in our class is the delta H for us is known as the heat of reaction. So the heat of reaction. Now, arrow 2. It is similar to arrow 1 and arrow 5 because it starts at the x-axis and it climbs all the way up, and it reaches the peak of the hill. So what this is known as the potential energy of the activated complex. You don't need to be able to define or explain what the activated complex is. You just need to know it's the potential energy of the activated complex. You might be asked on a part 2 question, on the given or provided potential energy diagram, place an X to represent the location of the activated complex. So be able to put an X at the peak of the hill. Now, when we take a look at arrow 3, it starts on the platform of the reactants and it extends all the way up to the peak of the hill. So it starts on the reactants platform and up to the peak of the hill. This is what is known as the activation energy. So the reactants have the ability or the potential to make the products, but a lot of times they need a little push to get it going. So the activation energy, this is the push to start the reaction. So I'll keep it simple. Now, arrow 6, it is very similar to arrow 3 in that it starts at the platform of the products and it climbs up to the peak of the hill. So it is also an activation energy, but it's the activation energy for the reverse reaction, the products to reform the reactant. So the activation energy of the reverse reaction, meaning for the products to remake the reactants. Taking a look at the diagram down below, yes, I have some typos, fix them in your notebook. We'll take a look at an endothermic process. So the platform closest to the y-axis always represents the location of the reactants, and the platform farther to the right, always represents the location of the products. So when you look at the hillside lengths, you notice that the reactants up to the peak is much longer or bigger than the slide down to the products. So in an endothermic reaction, the reactants have to absorb more energy than they release in this type of reaction. But the end result, take a look at where the products platform ends up. It's above or higher than the reactants. So the products stored energy or potential energy is more than what the reactants have. The delta H is always final minus initial, so the product's potential energy minus the reactant's potential energy, so this value minus this value. Because the products have the larger PE value, you'll end up with a positive delta H. Okay, labeling the regions, very similar to the one up above. So arrow A starts at the x-axis, climbs up to the platform we labeled as R. So this is our potential energy of the reactants. Arrow B also starts at the x-axis, but it climbs all the way up to the top or the peak of the hill. So the potential energy of our activated complex. Arrow C is the region between the reactant and products platforms. So that is our delta H value, the heat of reaction. Arrow D starts back at the x-axis and it extends up to where the platform of the products are. So this is our potential energy of the products. Arrow 5 over here, it starts on the platform of the products and climbs to the peak of the hill. So this would be the activation energy of the reverse reaction. And the newly drawn in arrow 6, it starts on the reactants platform and extends all the way up to the peak of the hill. So this would be the normal activation energy, reactants making the product.